Hello. I'm really tempted to say good morning. This title worked a lot better the first time I did this talk last week at the ACCU conference, when I was the first talk in the morning. The title is a bit of a play on words, as I hope you've spotted. I've been told that some of my jokes don't translate very well, so I try not to make too many, but I can't guarantee that, so I have to watch out. I need to keep talking while this animation plays. This is actually animating. I have to watch very closely. So, introduce myself. I'm Phil Nash, developer advocate at JetBrains, as we said. So I work with the C++ tools, ReSharper C++, C-Line, and app code. If you don't know JetBrains, you can come and talk to us on the booth just outside. If you do know JetBrains, you can come and talk to us on the booth just outside. Very friendly. We can see the sun's rising now. Obviously, JetBrains have offices in Russia, in St. Petersburg, and here in Moscow. We also have an office in Munich, and I usually go there once a year in December, and we have the Christmas party. Last year, it was up in the Austrian Alps. This photo is actually from that visit just last December. I thought that was quite nice, so I'm glad I got to show you that. Now we're going to talk about error handling. And before we get to that, we need to do a little bit of history. Because, in fact, most of this talk is going to be about this proposal, P0709. Some of you may have seen this or heard about it already. Some of you may have heard me talking about it. Because this is not the first talk that I've done about this proposal. I've previously given this one several times last year. Optional was not a failure. Yes, it's another pun in the title. I did warn you. And this talk is really the sequel to that one. So how many people here have seen me give this talk? Just a few. So this talk is a sequel, so I'm going to dig into some different material, but I'm going to summarize what I talked about in that one at the start, so hopefully everyone will catch up. But actually, this is not the first talk that I gave with that title either. Earlier last year, I gave a talk with the same title in Swift at a mobile conference, because I do Swift development as well. And the reason I gave that talk was because Swift has what I consider one of, if not the, most advanced error handling strategies in any language. And that's quite a bold claim. And I don't think everyone in the Swift community fully appreciated that, so I wanted to explain why I felt that way. And it was all about the roots of how the error handling strategy works, and I took them through how you build it up from ADT-based error handling, which we'll talk about in a moment, and how we end up with this very comprehensive error handling strategy. And while I was doing that talk, I realized that we're actually on the same trajectory in C++. Going in the same direction. We have a lot of the same pieces already there. We just need some language level changes. So I decided to do a talk in C++ as well, on the same subject, even the same title. And the idea was to take everyone through those same steps and then say, and if we make these changes, we could go even further. But before I gave the talk, I heard about that proposal we just mentioned, P0709, from Herb Satter. We'll talk about that in more depth in a moment. And I realized that's exactly the same thing. Exactly what I was talking about. I wasn't the only one thinking along these lines, and that was reassuring. But I want to go even further back in history, because I've been thinking about error handling for quite a long time. And one of the first alternatives to exceptions that I came across was this thing called exploding return types. Who's heard of exploding return types? Not many people. Interesting. This was quite a few years ago that I first came across this. In fact, I think it was in this talk in 2007 by Andrei Alexandrescu, Choose Your Poison, Exceptions or Error Codes. And one of the slides from that talk, this one, he has a type called likely T that can hold either a value or an error. In this case, it was an exception. There was an exception. And you could test whether it held the value or the error. But here was the interesting bit. If you haven't checked whether it held a value or not, the destructor would throw. That was a little bit controversial even then. but that's where the idea of an exploding return type comes from. Forces you to check your errors. And I like that idea, and I ran with it. Actually, I did a bit more digging, and I traced this idea back to this Usenet post from the year 2000, exploding return codes on comp lang C++ moderated. Ken Hagen starts out of intellectual curiosity. Interesting turn of phrase. Here's the important bit. In the destructor, if you haven't checked, throws an exception. But actually in this thread, it referenced even earlier work from James Cans and Lisa Lippincott. And in fact, James's comment in the thread suggests that his version was even before we had exceptions in the language. So this idea has been around for a long time. And talking of Lisa Lippincott, I particularly liked her comment in the thread. Let's not repeat the mistakes of the past. Model the copy construction and assignment on the current auto pointer, not the old broken one. Simpler times, eh? Moving forward a little bit, back to Alexandrescu. In 2012, he did another error handling talk, systematic error handling in C++. And in there, he presented an evolution of that type that we'd seen earlier. Had the same idea, can hold a value or an error type. And if you tried to get the value out without checking it first, it would throw the stored exception, now in an exception pointer, as before. But it didn't throw in the destructor. Because now we're in 2012. C++ 11 is out. C++ 11, destructors are no-throw by default. And in fact, that caught me out because I was using these exploding return codes, and because of the way we'd done it, that pretty much broke all my code, and I had to redesign it, which was probably for the best in the long run. But yes, we didn't use exploding return types anymore. But C++ 11 was out. It was now a lot easier to do this sort of thing more cleanly. You can have unions with non-pod types that have non-trivial constructors. So this was a much cleaner design. Interestingly, this was called expected. If that sounds familiar, it's because there is a proposal for stood expected, which is ultimately based on Alexandrescu's design. It's evolved a little bit. That's still on track to go in. I'm not sure if it's actually been accepted in yet. I don't think it has just yet. That's probably going to go in, if not in 20, in 23. And that's the sort of the ultimate point of this thread in C++. But these ideas are not unique to C++ by any means. It's just a handful of languages that I'm familiar with that have something similar. The most general one, the Haskell either type. I won't mention Rust. We have Kotlin, of course. Swift again. I mentioned Swift earlier. Interesting that it's only just got this result type, which is basically the same as expected. Just recently in Swift 5, only launched a month or two ago. Actually, what Swift calls Swift error handling is sort of based on an evolution of this. It's interesting it got that first. It's only just now got the result type. So what is stood expected, and how does that work? Let's have a look at an example. Here is a function that takes a string, or a string view in this case, tries to parse an int out of it, and it returns a stood expected of int, or, in this case, chosen stood domain error. You can use any type there. It doesn't have to be an exception type. The implementation is not that interesting. That's not the point of this. The point of this is that return type and how you return it. You return stood make unexpected, so that will help a function to make sure it's unambiguous, and then you pass the error type. So it's just normal control flow. We're just returning errors the same way that you return any other value. But this type can hold either the value you actually want or the error. So how do we use this? Well, let's actually, to make it more interesting, before we get to that, here's an example. So we're calling our parse int with some string. We get a result. We can check the result. So it has a Boolean operator overload to make that a bit nicer. And if it has a value, we can just dereference it like a pointer or like an optional. Works just like an optional if you've been using that. But if it has an error, we can get that out using .error. And because in this case it was an exception, I can do .what on that to get the string out. Whatever the type is there, we've got access to that type. But here's the problem. The yellow highlighted code is the happy path. The rest of it, everything in red, is the boilerplate coming from the error handling. And this is only one usage. When you start to compose these things, as we will in a moment, you can see it actually gets a lot messier. So in fact, let's do that. Let's introduce another function, which takes an integer, or 2 integers in fact, and again returns a std expected of int or an error. And in this case, it's just, because it's doing a divide, it's just checking for division by 0. Again, the actual example is not that interesting. It's just the error handling. And let's, just for fun, add one more. This function just takes an integer, adds 1 to it, no error handling. That's fine. So we have these 3 functions, and we want them to work together. Now we've got to write code like this. This is what I mean. It starts to get very messy very quickly when you use return code-based error handling. Now you might say, okay, well, if we're returning out of here, we can use early returns to clean it up a bit. Let's try that. It's a little bit cleaner. That's still a lot of code just to handle all the errors. And this is pretty much the leading edge of what we can do with this sort of error handling in C++ at the moment. In fact, this is not even standardized yet. This is future C++. So it's about this time we need to talk about monads. Specifically, this proposal, monadic operations for, well, it stood optional here. Simon Brand, who proposed this, has made no secret of the fact he wants the same operations for stood expected as well. We don't need to go into what a monad is right now, just that it has these operations. So here's the key point. I propose adding transform and then and or else member functions to stood optional and stood expected to support this monadic style of programming. So if you do know what a monad is, or you've used this sort of thing before, you might want to think of transform as map and then as bind. They sometimes come by other names as well. And the or else, in terms of error handling, you can think of that as like a catch. This is the thing that will get called if you have an error, and you can put it at the end of your sequence of operations. So let's have a look at how that looks for our example. So here's where we got to. It's the example with three functions being composed, trying to compose them together. They're not really composed yet. If we imagine we had those operations on stood expected, this is how we might now do it. Let me just show you that again. That's what we had, down to that. I think you'll agree that's a lot less code, and arguably cleaner code. Once you get used to the extra syntax, easier to reason about. There's no if statements, there's no extra checks in there, no dereferencing. It's hard to get that wrong. I think that's a lot better. But we still have some boilerplate there. It's less than before. The ratios are getting better, but about half of that code is just error handling boilerplate. So what makes this worse is when you compare it to the competition. Okay, we have C++. C++ has exceptions. The same example using exceptions is like this. Let me show you that again. Right. Notice it's not just the usage code that's changing. The top, our return type is simpler as well. That's so much less code. There's so many less things to worry about. Yeah, and we're saying, no, this is where we want to be. This is where we're going. Well, there are reasons for that, and that was a big part of my previous talk, was to go into all the reasons why this sort of style, even with the boilerplate, can still be better in many cases. For a lot of people, it's the only thing they can do if you can't use exceptions. But it'd be really nice if we could solve this problem, all this extra boilerplate, to get something more like this. And that is what P0709 is all about. It's about having an exception-like syntax, that has all the characteristics of something like stood expected with those monadic operations. This is what it looks like, same example. Let me show you that again, because it's a little bit subtle. So, classic exceptions, new style exceptions. So, let's actually drill into exactly what the differences are. So, on our function, we have this throws keyword to qualify the function. So, we used to have a throw qualifier there. It's now deprecated. This is not the same thing. This is something that's statically checked and actually changes the meaning of the code you write in there. So now when you see that throw, that actually means something slightly different now. And at the call site, we have that try keyword. That's the thing that says, the thing after this is something that has the throws keyword on it. That can be statically checked. So much like with the stood expected and the monadic binding, everything is known at compile time and checked. You can't get the wrong thing. Unlike classic exceptions, we can actually see where the errors can come from. So let's put the usage code in its own function so we can see how it composes on. So this function also has the throws keyword because an exception may propagate out. If we use a slightly different function, we can use try and catch, just as before. They have the same meanings, so I've given them a slightly different highlight color. Notice I've made this function no except because no exceptions can come out. That's a slight correction on my previous version of this talk, where I suggested it still needed the throws keyword. That was incorrect. So just to fix that. So how does this connect with what we talked about with stood expected and monadic binding? Here's what all those keywords really mean. When we see that throws qualifier, whether or not we have a return value, you can think of them as mapping to something like return value of stood expected of that type, which could be void, of course. And this special type stood error, we'll come on to that in lots more detail in just a moment. So it's as if you wrote return of stood expected. And then when we wrote throw, inside a throws function, it's as if we wrote a return make unexpected of that error type. And that try keyword, just those 3 characters, gives us all of that monadic binding sugar, or if you prefer, that fully expanded version. That's writing a lot of code for us, effectively, but it really means basically the same thing. Doesn't mean it actually writes this code for us. In fact, what the compiler can do, because it knows your intention even better at this point, it can be even more optimal about it. For example, in the stood expected, you need a discriminator variable in there to say whether it's the value type or the error type. Well, that can actually go in an unused bit in a register on the return channel. So you basically get that for free in terms of storage. So space overhead of this is, in most cases, 0. The runtime overhead is pretty close to 0 as well. In fact, compared to what you could write by hand, it's at least 0, maybe less, is the claim. That's not the case with exceptions. We're not going to dig too much into the cost of exceptions in this talk, because that's what we talked about before. But for many people, the performance cost, the non-determinism cost of exceptions are showstoppers. And people that are nodding know exactly what I'm talking about. But we don't want to throw away all the good stuff. That's what this proposal gives us. So let's go back to our example. And the one bit that we haven't really dug into, and I haven't covered in the previous talk, is this type here, stood error. What does that actually mean? So we've mentioned that it's a value type. The thing that we're throwing is a value. This is the biggest difference with classic exceptions. With classic exceptions, we're throwing objects that have to be allocated on the heap, although there are some implementations that somehow do it on the stack. Doesn't quite count because they have their own problems. In general, it's allocated on the heap, and when you catch it, you have to do RTTI to work out which catch handler to visit. So you pay those 2 big non-zero costs. That's where the overhead comes from. And then there's potentially unwind tables as well. That's another story. Here we're throwing values. And as we've seen, it's the same as returning those values down the stack. So much more lightweight. But what sort of value is it? So there's actually another proposal, a supporting proposal, P1028, full title, SG14 status code and standard error object for P0709, zero overhead deterministic exceptions. So right in the title it says this is a supporting proposal for the so-called static exceptions proposal. But don't let that fool you. This proposal stands on its own. It's very worthwhile in its own right, as we'll see. Even if we don't get P0709, this will be a very worthwhile proposal to go in. So let's dig into why. Right in the opening paragraph, it says, this is a proposal for the replacement in new code of the system header system error with a substantially refactored and lighter weight design, which meets modern C++ design and implementation. So it's a replacement for something we already had. So we'll have a look at that in a moment. Let's come back to the code. So we're talking about std error. What is std error? It's actually a type def we're using for this thing. So it doesn't look so simple here. We're going to unwrap this, but in order to do so, we need to talk about what this is a replacement for to fully understand its role. So let's go back in time again, back to C++ 11. This is how long we've had this. This is std error code. That's from the system error header. So who here is familiar with std error code? So a handful of people, but by no means everyone. It's been in the standard since C++ 11. It's a really useful type, used extensively in the file system API. That's the main reason it was introduced. It was actually split out from there. And also the networking TS. No coincidence that both of those libraries originally came from Boost. Boost file system and Boost ASIO, which is also where error code came from. So if you've used Boost, you may have used it as well. And this is this simple value type, usually represented by an enum. That's actually an integer, to represent system error codes, but also can interoperate with your own error codes. It's a really interesting design. So we're just going to go into that a little bit now so that we can see how it's evolved. So here's a sketch of what it looks like. Just looking at the data members, you've got an integer, which you can think of as like a stand-in for any enum, because any enum can convert to an integer. And this pointer to an error category. So we'll have a look at those in a moment. It's got lots of methods. I'm just going to highlight a few of them. For a start, it's just got these accessor methods. So we've got access to the value itself. And the error category, by reference, is to the pointer, but other than that, it's just straight accessor. So they're clearly important parts of the interface. And we'll come back to the other methods in a moment. But let's have a look at what this error category is then. So an error category is really a domain for errors that will be described in an enum. So you have an enum, such as this ERC, which is actually defined in the standard. And ERC just contains a mapping of all the POSIX error codes. So this is sort of the default system error code. And then you can have another error category, another domain, which could be your own type. So your own enum you define could be any values in there, no matter how silly they are. These are separate categories. And then you can provide your own class derived from error category to actually handle those different types. So some people call this the handle in a context idiom. So you have an integer representing an enum. You don't know what the enum is, but the error category does, that's associated with it. So your error category knows about your enums. And it's got some methods on there. And what's interesting is that these equivalent methods allow you to provide a mapping between different error categories. And that mapping doesn't have to be one-to-one. It could be one-to-many, many-to-many, Not all of them have to be supported. All depends what makes sense for your errors. That means you can treat errors in one category as if they were errors in another category, which for comparison purposes really makes a lot of sense. It's what makes this a really interesting design. So that's how the message method works. It calls into message on the error category. The error category knows what the enum is, and so can therefore provide a stringified version of it. The other interesting thing is that if you compare two error codes, you'll get an exact match comparison if you compare them using equals equals. But if you compare an error code with something called an error condition, which is basically identical to error code, but it's just a different type, it'll do this semantic comparison, and that's where those equivalence functions come in. So you can compare very easily between different error categories using error condition. Unfortunately, that's a little bit subtle, and not everyone fully understands how or why that works. So it's a really useful facility that's unfortunately a little bit clouded. So in fact, there's quite a few problems with stood error code. Remember, we're talking about the C++11 facility. One of them is that the way it's specified in the design is that those error categories have to be implemented as singletons. And the reason is because comparing error categories is by pointer. So every error category must have a unique pointer address. That implies singletons, which most of the time is fine, except if you have an error category defined in a header-only library, and then that header-only library is included in multiple dynamic libraries. Now your same error category has different pointer addresses. The whole thing falls apart. It's a rare case, but it happens. There's other problems. There's a dependency on stood string. Might not seem like a big problem. We use stood string everywhere, don't we? But actually, stood string is quite a heavyweight dependency to have if you don't need it. It pulls in things like locales and IO streams and other heavyweight dependencies. So if you can avoid it, it makes the whole thing much lighter weight. And in this case, using error code is something that people tend to do when they can't use exceptions because of the cost of them. So we're already working in a constrained environment, and now we're forcing these extra dependencies on people. So that's a shame. It has this conversion to bool, which looks really useful. You want to see whether it has a success value or not. Unfortunately, that's not what it does, at least not reliably. The conversion to bool only tests whether the value, the integer, is 0. Now, whether that 0 actually means a success value or not in your domain is open to question. So it's not reliable, is therefore almost completely useless, maybe even dangerous. So that's a problem. It needs a separate error condition type. We mentioned it's basically the same as error code, but it's only there to disambiguate when you do an equals equals operation to say whether it's semantic comparison or strict comparison. And that's a little bit confusing. So that's a problem. Since it's defined in C++11, it's not const expr. Const expr was much weaker in C++11, and this was actually designed even before we had that, so none of it's const expr. Most of it can't be made const expr, mostly because of that singleton categories problem. So that's another problem. And then the error code itself can only be an integral type, which is fine for enums, but if you wanted to put some other payload in there, that's not so useful. And then in our minor nitpick, we said that an error category was a type of domain. Most people tend to find it easier to think of it as a domain, so why not call it a domain? Just a naming thing, but there we go. So here's the new type. This is what's proposed to replace it. Looks very similar on the surface. This is status code. So we have status code domain. That takes the role of the error category. So now we're calling it domain. Excellent. That's one of the problems fixed. But still a pointer to a domain. But the identity of the domain is not its pointer value now. The domain has to have a randomly at design time assigned ID that should be unique. So you can have multiple domains at different addresses that have the same ID. And notice this is the template, so the value type can be any type. To make this more useful for our purposes, we're going to constrain it in a moment. So let's reintroduce that type def that we saw earlier. Interestingly, this doesn't map to that type at all. So we've got status code, but this starts with errored status code. Well, for our purposes, we want an error only. This is stood error. So errored status code is identical to status code, except it's guaranteed to never contain a success value. That's checked in the constructor. So it's a runtime check, but once you have an errored status code, you don't need to check whether it has an error or not. It always has an error. So that simplifies things for our purposes. Now, to define the template part, the E, we can see it's this erased system code value type. So you might guess that erased is some sort of type erasure, and it is. And what it does is it takes its template argument and uses that as for the size of its storage. So it will store it in something the size of whatever you pass. And in this case, we're passing system code value type, which is another template, but by default, that's going to be an int pointer t, which makes a lot of sense. It's going to be an integral type as big as a register word. So plenty big to hold an enum, also big enough to hold a pointer. Now we can have other types of things held in there using type erasure rather than type punning, which is a bit safer, and not undefined behavior, which is nice. So you can think of error code as actually being like this. Sorry, not error code, stood error. So we have a domain pointer, and then we have some storage, which is the size of an int pointer t. And it's actually safer because it's this arrays type rather than an actual int pointer t. But effectively, this is what we have. So it's actually very similar to what we had before. It still fits into two registers, which is what stood error code did, which is useful for our purposes. But it has all of these properties now. As we said, minor point domains are now called domains. Easy to understand the category. And those domains are based on, as we said, random 64-bit IDs. That's random at design time. You have to choose them yourself. So we don't have that pointer comparison problem. The value can actually be any small, trivially copyable or trivially movable type. We'll get onto what that means in a moment. That's really important, because that means that we can copy these things around by value, effectively using memcopy. We don't have to recurse into the arrays type and do copy or move construction. We can just copy the bits, which, remember, are just two registers. So that's really important. We don't have the stood string dependency. In fact, as proposed, it has its own string ref type. Not sure that's going to survive going through the committee, but it's with very good reason. So we'll see how that plays out. It's mostly const extra now. We don't have the problem with the category pointers. Doesn't have the bool conversion, because that was unsafe. Doesn't matter in our case anyway, because we always have an error code. We don't actually need it. And comparisons are always semantic. We always do an equivalence comparison. So we don't need a separate type to represent that. We just have stood error, and we can compare them. It's always a semantic comparison. So that basically addresses all of those issues that we mentioned before. Fixes them all. That makes this an even more useful type, particularly, as I say, that trivially copyable, trivially immovable property. So there we go. Fits into two CPU registers, as we say. So about this movable thing, so making it trivially copyable is enough to say, well, we can copy it from one location to another without having to call any methods. But if you have a move-only type, like a unique pointer or an exception pointer, then you won't be able to store that in there. If we had a way to say that a type was trivially movable, i.e. if you do a move, it just moves it, just copies the bits to another location in memory, then it would allow that. So there's another proposal. P1029, move relocates. In fact, there's another proposal as well. Either of these would actually serve the purpose. So what's the difference? So the move relocates one, the first one that we mentioned, that just defines an attribute that indicates whether a move is trivial, i.e. you can just use memcopy. Whereas P1144, object relocation in terms of move plus destroy, is more ambitious. And in fact, the attribute is the optional part, but that could serve the same role. It also has the ability to detect movability using, or trivially movability using a trait. And it's actually two memcopies. You can memcopy from, and then you memcopy a default constructed instance into to reset it. So that's the destroy part. And the idea is that hopefully this will get around previous objections to what we call destructive move. This is the next in a long line of destructive move proposals. And that may end up being the sticking point, which is why we also have the other proposal. So we should be able to get at least one of these through, hopefully. And they're not completely incompatible. It also defines the concept of relocatability as well, just so that we can talk about it in the standard. And it's got some algorithms in there as well. So if we get one of those two proposals in, along with the Studera proposal, then we can use that value type to represent not just those enums representing system errors and your own types of errors as just simple IDs, but we can also put things like exception pointers in there. And that really then makes it much more flexible and also allows us to interoperate with classic exception handling. So that's why these proposals are important as well. So that's Studera. Let's have a look at, these are the proposals we've been looking at. P0709 is the big one. Zero overhead deterministic exceptions throwing values. So that's what gives us exception-like syntax, but with the semantics that are much closer to returning stood expected, but better. To make that really work well, P1028 defines the stood error object we've just been talking about, fits into two registers, can represent an enum or a pointer type, including exception pointer. And then the bottom two to talk about trivial movability is what makes that efficient and what makes that zero overhead, as it says at the top. But there's another proposal that comes into this we haven't talked about yet, and we're not really going to talk about it at length. Just going to mention that this is also relevant. P0542 has been adopted into the standard now, support for contracts-based programming. Although there's a little bit of controversy going on around it within the committee at the moment. There may still be some changes yet, but if we have some form of contract to the language, the reason this is relevant is because it turns out that a lot of things that we currently use exceptions for are really logic errors. In fact, we have stood logic error as an exception type in the standard. And it's been said that that itself is a logic error. You shouldn't throw exceptions for things that really are bugs. Instead, you should define contracts to protect against those. And by default, contracts will terminate. You can actually define their behavior. But they give you that flexibility. So they're much more advanced than asserts, much more granular. For some people not granular enough yet, that might be one of the problems. But if you define these things in terms of contracts, which is what the idea is, change a lot of the standard library, choose contracts instead of throwing logic errors, that removes a lot of uses of exceptions from the standard library and from user code. So there's a lot less places left to have to use what we're calling static exceptions. And then there's another optional part to P0709, which I'll go into a bit more in the previous talk, where we talk about what happens when we run out of memory, heap exhaustion. And let's talk about, well, maybe the default should be we just terminate, because most code is not prepared to handle it. And in fact, there's a experiment, if you like, going on at the moment to try and get some data on just how well people do handle heap exhaustion. Because the theory is a lot of people claim to, but in practice don't. It's actually really difficult to test for. So that's an ongoing thing. Well, we'll see how that works out. But again, once we remove contracts and we remove heap exhaustion exceptions, bad alloc, there's only a handful of places left in the standard that actually throw exceptions. And they could easily change to static exceptions. And then we could have a complete standard library that doesn't use legacy exceptions at all. Meaning that people that can't use exceptions will be able to start using exceptions. And we'll all come together as a big happy family. So that's the end of this material. But if you've got questions, I'll be happy to answer them now. Thank you.
Yes,
I've got a mic coming.
Thank you. I have a question about fno-except. Like if you use traditional exceptions, you have a way to turn them off in the compiler. Will there be a possibility to turn them off for std expected, and will it work as fast as I didn't write like all this stuff, like if e equals 0, then throw my std logic error, which is not like actual throw, which just returns std expected with an error. So, did you understand the question?
I didn't quite catch all of that. It was about being able to turn off exceptions, did you say?
Yeah, can I turn off like new way exceptions using compiler flags?
Turn off new style exceptions using compiler flags.
Yeah.
I don't think there's any talk of that. So you're referring to the fact that we can now currently turn off old style exceptions using fno exceptions or whatever the flag is for your compiler. I think there's some debate over what that particular flag will mean in a world where we have new style exceptions. Whether that will just turn off legacy exceptions but allow you to use new style exceptions, or whether it turns off everything. And I think the feeling is it would only turn off legacy exceptions because the reason that people turn off legacy exceptions don't apply in the new world. But that's still an open question, I think. We certainly would want the ability to say, compile this without legacy exceptions, but with new exceptions. That would be really important. But exactly what that looks like, that's more of a bike shedding issue, I think.
Okay, thank you.
No problem.
Hi, thank you for an interesting talk. And I not really understand why do we need new attributes for something that looks like we can understand from the type itself, right? I'm talking about move.
So the
movable and relocatable.
Come back here. Yeah, move relocates, and there's also one in trivially relocatable here. So the attribute in P1029, the first one, that's the only thing it defines. It just says, I'm certifying, or there is a term for it, that this type is relocatable when you do a move. Whereas the more ambitious one will actually infer it where it can. And then the attribute is only needed when the compiler needs a bit more help to make that assessment, which is why it's optional in that paper. But that requires a lot more complexity on the compiler side, plus the whole part about destructive move, meaning that that proposal may not get through based on historical trends. So this one just tries to keep it simple and just says, well, this is all we need to make this work. So if we have at least that, then we can do what we need now. But it still leaves the bigger question of, can we make types more efficient by default? Which is what the other proposal tries to address.
So it's some kind of compile time check, like concepts?
Sorry, repeat that?
This attribute will serve like compile time check, like concept?
So this one, there's no compile time check. You're just telling the compiler, I'm saying this. And if you're wrong, then it's undefined behavior, of course.
Cool.
In P1144, there's an associated trait is trivially relocatable, which tests whether either the compiler thinks it is or you've marked it as such. But in the case where you've marked it as such, there's no way for the compiler to then say, actually, no, you're wrong. There may be static analysis tools will do that. I don't know yet. I think that's another of the open questions.
Thank you for your talk. I have a question about usage of keyword throws and try. What will happen if I will call these functions without a try keyword for it? It will work as usual, or it will throw all exceptions. What will happen?
So if you call a function that has the throws keyword, if you don't use the try keyword when you're making the call, then it won't compile. But if you... One thing I did skip over is that try keyword is actually an optional part of the proposal. We may not get that part. I think it'd be disappointing if we don't, because that's the thing that makes it easier to reason about, and it's checkable by the compiler. So in the version where you do have the try keyword, that will be checked. If you don't have a try catch around that, it propagates out as before, in which case you need the throws keyword on your function. And again, that's checked by the compiler. So if a function that doesn't have throws calls a function that does, and you're not catching it, then that's checked by the compiler. So it's safer at compile time. Does that answer your question?
Yes, thank you.
Can you go to the slide 47?
Which one, sorry?
47.
47.
Yeah, I think so. Yeah.
This one?
Yeah. So you mentioned that it would be a real shame that if we got without the try keyword, because it communicates where a fallable function can reside.
Yeah.
And here we have three functions with a single try keyword, and we have no idea which one can throw.
Because on that line we've got, well, in this case, two calls that have throws. Yes, we don't know which one, but it doesn't matter. The try is for the whole expression.
Yeah, but in that sense, you could write try for the whole function, and then try keyword doesn't make sense. For me, it would be much prettier if try parseInt was and try divide was explicitly stated in the line instead of just at the beginning.
That would be another way of doing it. I don't think that's necessary. I don't think it gives us enough value to be worth the extra noise. I think this is the right balance of adding a little bit of extra noise to give you some signal as well. And maybe you disagree, and this proposal is still open. So come to the standards meeting and vote on that.
Who's going to pay for that?
Thank you for your talk. I have two questions. The first, for this slide, the first is this try-catch construct is a regular try-catch construct that we know today? So it really catches an exception. And the second one, can we avoid new features in the language and just change the implementation of current exceptions so that they just return error code? For example, we use the special register for error code. Thanks.
So very good questions. So the first one about the try-catch here, do they have the same meanings as in current code? And the reason that's a particularly good question is because I got this wrong when I gave this talk last week. And I said they actually had slightly different meanings when they were within a function marked with throws, which which is why I've marked this one no except instead. In fact, after discussion with Herb, I agree that no, they have the same meaning. It's just that if one of your catches or your only catch happens to catch a stood error, it's going to catch that by value, and it's going to be via the return channel. But you can still write, even here, extra catches that will catch dynamic exceptions as well. So you can mix them, which is going to be very useful as we start to roll this new style out without having to do everything all at once. The second question, I'm trying to remember what the second question was now. Oh, yes. Can we change existing exceptions to use this model? To some extent, we can inch it in the right direction, but we can't go all the way. Because of the way they're currently defined, if we did change it, it would be a breaking change for a few reasons. One of them is that you can have multiple exceptions in flight at the moment, and we have various mechanisms to deal with that, and there are things that rely on that. And there are other reasons as well, which I can't think of off the top of my head, but they are written up in the proposal, so do read that. There's a whole section on how that's being considered. Where you can get to would be better than where we are now. That may even be worth considering on its own. But it won't cross that divide where people that currently turn off exceptions will be able to say, okay, now we can turn them back on again. Because for those people, it has to be below a certain performance threshold, which is significantly lower than where it is now, and it has to be deterministic and not allocate memory. And it's pretty much impossible to do those things as exceptions are currently specified, and changing that would be a breaking change. So this is, in a way, that breaking change, but in a backwards compatible way, which also gives you some extra nice things as well. For example, the throws keyword, which is statically checkable, is, I think, an improvement, because now we can see in the code which things may or may not throw exceptions. So while it could be worth tuning up current exceptions, that's not going to get us to where we want to be with this proposal.
Test. Okay, thank you for a good talk. Maybe I just haven't heard correctly, but can the new way of exceptions work with disabled regular exceptions? Can I parse an error without a catch keyword?
So you want to interoperate this mechanism with the stood expected style, you mean?
No, I want to disable RTTI and disable exception and use only this new proposal.
Yes, you could definitely disable legacy exceptions, so completely outlaw them, and then use this mechanism only. That's very intentional.
And that try catch will work. It doesn't really throws and catch. It's just like a syntax.
Yeah, so you could, if you disabled exceptions with no exceptions, and you had a try catch here that catches a stood error, and you call a function marked throws, that will work. That's exactly how we want it to work, because of those people that will currently disable exceptions. We'll want them to be able to use this. Because we're never going to be able to get rid of legacy exceptions completely.
So, yeah, the last one, I think.
Thank you for your presentation. My question is, can we build exception hierarchy and, for example, catch some more specific exception by generic type, by parent type? I mean.
So yeah, in a way, we lose the ability to catch exceptions at different points in the hierarchy. Except we don't, because if you remember, the stood error comparisons were semantic. So if you define your exceptions, your error levels themselves as a hierarchy, so more specialized forms will also match with less specialized forms. You can get that back. It's entirely up to you. As it happens, most of the time, most people don't catch different types in a hierarchy. It's useful sometimes. Most don't. So only opting into that when you need it explicitly, I think is a better thing. And it's by value rather than by type. It's the by type thing that implies the use of RTTI.